Recently we've learned that with compound interest there's a formula a equals p 1 plus I to the exponent n. Well, there's another formula which says that p equals a times 1 plus I to the exponent negative n. This is obtained by simply reworking the first formula and thereby making the exponent negative. Well, again, just like in the last questions, the a stands for the amount after the compounding occurs. The p stands for the principal, or the amount that was in there prior to the interest occurring. I stands for the interest rate per compounding period. And to do that, we use the same table that we used in the last question. And we remember the acronym AIRHEAD, which means annual interest rate has to be expressed as a decimal. For example, 5% is 0.05. And finally, we know that n is the number of compounding periods, and we use the table for that. So our first question that we're going to do today involves Carly. Today, Carly has $4,417.27 in her bank account. She made one deposit 3 years ago and never made any withdrawals. The interest rate was 2.5% per annum, compounded semi-annually. We'd like to know how much did she initially invest. Well, we know that the final amount that occurs after all the compounding is $4,417. That's the amount that occurred 3 years later. So we have A equals 4417.27. The principal amount, the prior amount, is what we're looking for. We don't know that right now. Little letter I is 0.025 because it's 2.5%. And we divide that by 2 because we're talking about semi-annual, and that's what our table tells us to do. So little letter I will equal 0.0125. And finally, n will equal the number of years, which is 3 in this case, times 2 because of semi-annual compounding. And so we get the number 6 for n. So we plug them into our formula. P equals a 1 plus I to the negative n, and we plug numbers in. A is 4417.27, little letter I is 0.0125, n is 6, so since we're going negative n, we're going to go negative 6 in this context. We evaluate our bracket, 1.0125. We raise that to the exponent negative 6, and since the exponent is negative, we see that we get a smaller number, 0.928174876 in the bracket. Why so many decimal places? Well, we would like to get our answer correct to the nearest penny. When we multiply that number by 4417.27, we get 4099.999. Now, clearly, somewhere up here in the question, there is a bit of a rounding error, and what we really want here, when we round $4,099.999, we know that this needs to be rounded up to 00, and this needs to be rounded up to 4100. So our final answer is 4100, and we can make a therefore statement. Carly initially invested $4,100. Okay. We move to our next similar type of question. If that didn't make sense, maybe this one will. We see that Kevin has $1,210.81 in his account. He made one deposit 5 years ago at 3.9% per annum, and it's compounded annually. He never made any further deposits or withdrawals. That tells us that the money is entirely due to that initial deposit. We want to know how much he initially invested. Well, we know the final amount is $1,210.81. We know little letter I is 0.039. We don't know what the initial amount invested was, but we know that the n value will be 5. Now, why don't we divide or multiply with the letter I and the letter n? Because we see that when the compounding occurs annually, which it does in this question, there's no dividing of the interest rate, and there's no multiplying of the letter n, of the number of years to obtain the letter n. So P equals a 1 plus I to the negative n. We're going to input 0.039 for I. We evaluate the bracket. And then we use our calculator to figure out 1.039 to the exponent -5. We use a lot of decimal places because we want to be accurate to the penny. That's 1,210.81 times 0.8258900103, which comes out to 999.9959966, which if we round up to the nearest 2 decimal places actually becomes $1,000. And so we can say that Kevin initially deposited $1,000.